Okay, so this is what we're doing. I'm assuming, and I hope I'm assuming correctly, that you are, you've been in energy, maybe you're new to energy efficiency, that's okay. Or maybe you are, you've been around for a while, but you just haven't done a lot of HVAC. Or you haven't, you hear all these terms, but you're not really sure what it is and what all these different things mean. And so what this talk is going to kind of fill in those gaps that I'm thinking or I'm imagining you might have. They're not going to be, I'm not going to, do any math, which I guess is good. I'm not going to go into, intense engineering detail and show you too much that's too deep. This is going to be more of a, let's say, beginner intro levels course, but I think that's what, I'm hoping that's what you logged in for. So I'll tell you what we're going to talk about. So number one, I'm going to start on something which, maybe you already know, but there's some of this stuff later that you probably don't know. And that the first topic is the refrigeration cycle. It's pretty important, I think. And we're not going to spend too much time on it, so don't worry, I'm not going to get too geeky on you. The next thing I'm going to go over is some of these smaller HVAC systems. Now, when I mean HVAC, I'm not really going deep into chillers and boilers at all. This is mostly air handlers and things that heat and cool air and dump it into the space. So I always, when I was first starting, and actually still, what I find really problematic doing HVAC, audits and whatever is, you see these boxes and they all look the same, these boxes on the roof. It's like, well, what is it? Is that a heat pump? Is that, a rooftop unit? Is it a package unit? Is a, what is it? Does it do air conditioning? Does it heat? And we're going to go over that. And then we're going to go over the bigger systems, real air handlers and the different types of air handlers. Finally, we're going to go over economizers, which you probably already know about, and then some HVAC ECMs, which will probably make sense once you understand how these HVAC units work. Okay, so what we're looking at here is the refrigeration cycle. If you guys took thermodynamics in engineering school, then you went over all of this, and this might be a little boring, or it might be a good refresher, I don't know. But to me, this refrigeration cycle, I mean, when I first learned it, I didn't really grasp how important it was. This is really, to me, one of the most fantastic inventions that humanity has ever come up with. It is purely ingenious, if you ask me. It is amazing. So, when people don't really think about it, or I didn't really until I took the class, but, a refrigerator, what does it do? It takes heat out of a cold place and dumps it into a warmer place. That's crazy. It's just crazy how that works. And it's based on this whole refrigeration cycle, I guess. There might be another word for it. I don't remember what it was, but we'll just call it refrigeration cycle. Okay, so basically, how it works is, I guess I'll start with a compressor. There's this line that goes through everything. You'll see that this pointed line that goes to these different, units, the compressor, condenser, expansion valve, etc. Well, so if we start the compressor, what does that do? It compresses. There's a refrigeration fluid, a refrigerant that goes through those lines. Okay. The compressor, what it does is it compresses or adds pressure to that fluid, and when things get under pressure, their temperature goes up. It's just basic thermodynamics law. So, if you really think about it, when the weatherman says, oh, there's areas of high pressure, that usually means it's going to be hot. Areas of low pressure, it means it's going to be cold. So there seems to be this relationship between pressure and temperature. So when the compressor compresses the refrigerant, you end up with really hot refrigerant. And it goes through this thing called a condenser, which is the top of this drawing. The condenser, what that does is it's like a radiator of your car, but on a refrigerator, it is the coils in the back of your refrigerator. And what that does is now that fluid is really hot and the air is less hot, so the heat from the fluid in the coils just goes out into the air and it cools down that refrigerant. Then the next step, so that we still have high pressure, but the temperature isn't as hot, it's warm, and it goes into an expansion valve. And what that does is it releases the pressure. So now the pressure's been released, things can get cold. And since we lost a lot of heat in the condenser, it gets really cold. And then it goes into what is called the evaporator. Now in your refrigerator, the evaporator are all these coils that you don't see, but those are in the freezer unit of your refrigerator. A lot of times, I don't know if it's in all models, but certainly a lot or most models, it's only in the freezer that they have these coils. And these coils then will, so it's the same thing. It's just like the coils on the back of your refrigerator. They're just in the walls of the refrigerator. And these coils are so cold that they're taking the heat from inside the freezer box, and the heat is going into the coils. So is that right? Yeah, it is. And so then it goes through, that's the evaporator. So now we have, things are still at low pressure, but it's a warmer temperature, and it goes back to the compressor, which, you know, will compress it, and now it's really hot, et cetera. And then we just keep going through that cycle again. So here is that same refrigeration cycle, but what I've done is I've kind of added the refrigerator part in there. So you can see at the very bottom where the heat is transferred from the freezer to refrigerant loop at the evaporator. And at the top, the heat is transferred from the refrigerant to the outside air, and that's on the back of the refrigerator. That's the condenser. Now, I can't see your faces, and maybe, you know, this is all old news to you, but to me, this is brilliant. Absolutely brilliant. I mean, if you think about, you know, humanity, someone came up with fire, you know, and flint and metal and making fire, but, you know, this is really cool. But we'll take that off. Let's just move on. So this is really a lot of how the whole HVAC thing works. All right, so I guess the last slide we were looking at it in refrigerators. Here we're looking at it with rooftop units. It's the same damn thing. So in rooftop units, or let's say package units, they have these things called DX coils. DX coils, it just means that there's refrigerant. They're not using chilled water. So it's in package units, they actually have this entire cycle where, so let's start the condenser. You see the condenser coils, shoot, I don't have a picture to show you right here, but there are condenser coils, and often there's a fan that's going to blow, and then it blows the air through those condenser coils. It does it's the rejection of the heat from the system, but it has all the rest. And so this evaporator at the very bottom, instead of it being in the freezer, it is the cooling coil. And so the outside air or mixed air, or return air, whatever that's blowing through the cooling coil, then goes down to a low temperature, maybe 55 degrees, and then it goes into the space. One of the things that really, I guess, when I was new, and actually for a long time, it really confused me is, how do I know what's what? And so first I want to explain the difference between these, and maybe you already know these. It's real obvious what electric resistance heating is. It just means that, you know, there's coils. I guess they're wire coils. You plug something in and they get hot. And electric resistance heating is usually about 100% efficient. Now furnaces that takes gas or natural gas often, or maybe something else, but usually natural gas, and they burn it. And that efficiency, I don't know, that's maybe 65, 85%. But heat pumps are different. Heat pumps are using that refrigeration cycle I just talked about. What's cool about the refrigeration cycle is, you know, if you're talking about heating, we could do the electric resistance, we get 100% efficient. You'd think, gosh, you can never get better than 100%. Well, that's actually not true. That's what's so cool about a heat pump, because what it does is it uses that energy and it moves heat from cold places to hot places. And it doesn't, you know, the efficiency isn't 100%, it can get up to 450%. I mean, but the efficiency is often like 300%. In other words, for every watt of energy you spend, you're moving 3 watts of energy. So that's really neat. So heat pumps they're fantastic, except in cold climates. They're not very effective. That is, air-to-air heat pumps are not. What's interesting about a heat pump is what they're able to do here is they're able to, it's not really reverse the flow, but I think they move a valve somehow so the flow gets reversed. Gosh, I'm not doing a good job explaining this, but with a heat pump, you can actually use the same cycle to cool or to heat. So let's see, we have that at the very bottom, we have the heat is transferred from the air to the system. So I guess this is heating. Is that right? From the air. No, this would be cooling. So it's from the air, that would be the zone, to the system, or from the supply air to the system. So I'm looking at the bottom, the evaporator. So that would be cooling. But you can flip a valve and all of a sudden, now everything's moving the other way, where now the heat is the condenser becomes the evaporator and the evaporator becomes the condenser. And now we are, instead of transferring the heat from the air to the system, meaning to the refrigerant, we're actually transferring the heat from the refrigerant to the air. So it actually, it does the opposite. It's really cool, and that's what a heat pump does. So it uses the same cycle, but it heats and cools. All right, there's different ways to reject this heat. Now, the most common, or not most common, but one that's commonly used is an air-to-air heat pump, and that's where they just, they let it's coils, and then they might have a fan which blows air through the coils, and so they release the hot air or the cold air to the space. But there's also ground source heat pumps. And ground source heat pumps, they would have these coils in the ground, or they can be in the water. And those coils, let me say it differently. The air-to-air heat pumps are not very effective or efficient below 40 degrees because there's not a lot of heat in the air at 40 degrees. So it can't, grab a lot to put into the space. But if you've got a ground source or water source heat pump, the ground doesn't get that cold. It might get down to, 55 degrees or so. Even if it's, freezing up, at ground level, it's still kind of warm below. And so you're able still to heat with a ground source. Okay, so one of the problems I had was with rooftop units or these things on the roof is it was hard to tell what's what, okay? That was always a killer. So first off, on the left, you probably know this already, but on the very left of this, either one of these units, those are the condensing coils. And there's a fan usually inside of there, which is blowing the air through those coils, and that's how it rejects the heat. Let's move on to the next slide. So what a package unit is ideally, a package unit means that all the heating and cooling is made in the unit. That's the idea, okay? And so it would have what they call DX cooling, which means it has its own refrigeration cycle, but it also could have a furnace, okay? Now, a package unit might only do, cooling only, so it might not have a furnace, okay? But everything's supposed to be there. Now, an air handler, by definition, gets chilled water and or hot water. That's what the HHW is, heating hot water, CHW is chilled water. It gets it from boilers and chillers, and it has these coils, and then the air will pass through the coils, and we'll look at that a little bit later. But the big thing I wanted to get across here was that a package unit makes its own heating and cooling. The air handler gets it from somewhere else. And usually air handlers are big. They often handle many, many zones. And I guess package units could handle a few zones as well, but they're usually not as big. A fan coil unit is just like an air handler, but they're usually smaller. They usually only condition one zone. There's often no ducting, but like an air handler, they also will get chilled water and or hot water from boilers and chillers, okay? And they are simpler. They don't have reheats. They don't have humidification. A lot of air handlers don't either. But I guess that the main thing is there's no ducting. They're smaller. They usually handle just one zone. And then there's these MUA. That's a makeup air unit. And those are units that take 100% outside air. They may heat and cool it a bit, and then they just introduce the air to the space. They're often used in kitchens, and actually they're used in all kinds of different spaces. But what I didn't like when I was first learning HVAC was these are all fine definitions, except there are package units that, well, maybe they do take chill water from the chiller, but they have their own furnace, or what do you call a unit like that? Maybe it's not a package unit. And I guess in the East, they call makeup air units what people in the West might call air handling units. And then fan coil units, it's like, you can look at something, you think it's a fan coil unit, but they call it an air handler. So there's a lot of, the wording in the HVAC industry is not that clear, the terminology. And so a lot of people will call things different things. Okay, so here is a package unit. Well, the only thing I wanted to tell you here was, so one of the, it's not great knowledge. It's not showing that I'm some sage or anything, but it's something for an intro level, I suppose, is you see on the right-hand side of this, of the face that's showing towards us, there's this, gosh, what do you call that? There's a darker brown little section. You can see it's throwing off a little shadow, and it seems to be, it's a piece of metal that's coming out a little bit at an angle. That is an exhaust, okay? This has a furnace, and that's what that's showing me, is that has a furnace. Also, you can see there's this kinky wiry thing on the very left to the very right. So this kinky coily thing, do you see that, Tyler? That's it. That is gas going in. So there's two things to look for. You know, you can look for one or the other, but well, actually you should see them both. You should see gas and you should see an exhaust. And that tells you, okay, it's making heat. But sometimes, you know, you look at these units and you don't know, is it a fan? No, I'm sorry. Is it a heat pump or is it an air conditioner? Because you don't see any gas heat. And you don't know what the answer is. You don't know, and you just got to get the nameplate data, and you got to look it up. Just type it in and find out if it's an air conditioner or a heat pump. Sometimes you just don't know. This is an air handler, okay? So you can see on the right, there's all these pipes that are covered in metal. Yes, so that's chill water and hot water pipes going into this air handler, okay? How do I know it's an air handler and not a package unit? Well, I guess it's the chill water pipes, right? And the hot water pipes going in. Or actually, I don't know if there are two sets of pipes. This might be only cooling. I don't know. But anyway, that's a air handler. They have a lot more. They're bigger. They handle a lot of zones, and they get chill water or hot water from somewhere else. Okay, I realized I had missed this. Split systems. So split systems they use the same whole thing, but they're different than package units. So package units, they deliver chilled and cool air or hot air to parts of the building. A split system doesn't deliver any air. It delivers cool refrigerant, okay? And I don't have a picture of the other part, the evaporator part, but inside the building somewhere, there's just a fan, which just provides cooling. And so it has the coils in the evaporator. So let me say this differently. In the box on the left, or the picture on the left, or the picture on the right, these are both what are called condensing units. They include the condenser, which you can see, that's the coils, and then you have the fan that will, let's say, help transfer the heat to the air. But it also has the expansion valve and the compressor. All of that are in these condensing units. Okay, so that's why I circled all of that. And so then what we have is these lines. And so you can see on the picture on the left, there's a thick black pipe, or I guess you can call it a tube or pipe that is coming up. That is refrigerant, cool refrigerant. And you'll see there'll be two lines. One's going away from the condensing unit, one's coming back. Usually one's insulated and the other one isn't. Sometimes they're both insulated. So that's all the little ones. Okay, what I really want to go into, and this was supposed to be the meat of the talk, is these different kinds of HVAC systems. So these are air handlers, but I guess you can call them package units as well. They are often, I guess package units can do these things as well. So first, I'm looking at a single zone system. Now, what a single zone system is, it's basically there's one thermostat for the whole air handling unit or package unit, and it supplies one temperature of air everywhere. Okay, so you've often heard of buildings where, oh yeah, the thermostat's over in the secretary's office and she keeps it really cold, and so the rest of us in this building have to freeze. That's because they have a single zone system. So the way this works, OA to the very left, represents outside air. So we got outside air comes in, maybe goes through some filters. Well, of course it does. And then we have a cooling coil and a heating coil. One of those two is supposed to come on, or maybe both if it's dehumidifying. And then it goes through a fan, and this SA, supply air, will go to whatever zones it's cooling. That's it. Oh, and then we have return air, which I guess is really exhaust air. We're just exhausting everything. So this is a constant supply air volume. That means the fan doesn't vary. It's a variable temperature. it'll provide whatever temperature air the zones need, and it's very bad at controlling different zones and different temperatures. Here's a picture of that type of system from an EMS. So here we go. So this one's taking return air, not outside air. But you can see the air is going through a fan, a couple coils, and gets delivered to the zone. That's about it. Before it goes to a zone, it usually is in the ceiling, not always, but it would go through these things, which are diffusers. So this is the same type of system, but here I've got mixed air. So the only thing I've added is on the left, where you see that vertical, let's say duct, it says RA for return air. So what we have is we have outside air and we have return air, and there's these dampers, okay? And it says fixed. Well, these could be, yeah, I guess these are fixed dampers in this case. So it's taking some return air and some outside air, and then it goes through the same process. It goes through a heating, cooling coil, and delivers the same temperature to every zone. Okay, so what an economizer is, and you probably know this, maybe not, is economizers were a pretty cool invention, at least theoretically. And the idea was, if it's 55 degrees outside, and if we want to supply 55-degree air to cool the zone, why do we have to turn the chiller on? That's dumb. Why don't we just use the outside air and be done with it? Well, that's what economizers do. If it's cold outside, or if the outside air is cooler than the return air, then we'll just use that and throw the return air out, use the cooler air. And if we have to do a little bit of cooling, we'll do a little cooling, but we don't have to do as much. So economizers are able to reduce the amount of cooling, mechanical cooling that's done. That means cooling by the chillers, and it saves energy if they work. The problem we have with economizers is they usually don't work. It's someone said at a conference recently, I thought was hilarious, I never really thought about it, is, you know, economizers are a great invention, except for they've probably wasted more energy than they've saved. And I think he's probably right. You can walk into almost any building and know before you even, you know, assuming they've got 4 or more air handlers, you know they've got economizer issues. You just know, because they always do. So the difference here in this, this is the same pictures before. Oh, I had a couple pictures of dampers here. These are big dampers from big air handlers, but these dampers will open and close, okay? And these, instead of fixed dampers, I have an exhaust air, return air, and outside air damper, and they will modulate open and close. They all modulate together, so I get the same amount of air that's running through the supply fan, okay? But what we're doing is we're, you know, adding either all outside air, all return air, or a mixture in order to get the best supply air temperature. Okay, so here it is on a EMS picture. So I have return air up top, and it goes through some dampers. I don't have exhaust air here because the air is being exhausted some other method. But I have 2 sets of dampers that are working together, and it goes through a fan and coils and gets sent to the room. So this is where the only place I really talk about cooling towers and chillers and all that, and that is I want to explain how those really connect to the HVAC system. So, you know, I have this thing I call a cooling coil. Well, what a cooling coil is, and I think you know this, is the chiller makes chilled water. So it might make, you know, chilled water, it's maybe 42 degrees or 40 degrees or 45, who knows. And it goes through these chill water lines into the cooling coil and the air handler, and it goes back to the chiller. So then the air would pass through the cooling coil and cool down. Okay, the boiler is either going to make hot water or steam, and that is going to go into the heating coil. Okay, and that will heat the air up. Okay, so now the chiller again is using that refrigeration cycle, and remember there's heat that it has to reject. So instead of having that cooling or that condenser coil, it rejects heat with condenser water, and so it sends hot water to the cooling tower, which has fans, and then the cooling tower will drip the water through this, they call it cooling tower fill. I don't have a picture of it, but it just drips the water. You've seen it, and then the fans run, and what it does is causes evaporation, and when things evaporate, it cools things down. I think you know the feeling, having gotten out of a swimming pool and you stand outside and you get really cold. It's because when the water's evaporating off your body, it's taking all this heat out of you. And that's exactly what happens in a cooling tower. So then the water is cycling through the cooling tower back into the chiller, and that keeps I guess that removes the heat that the chiller is removing from the cooling coil. Okay, so this next system, we don't see these anymore. We saw them a few decades. You still see them. If you saw them a few decades ago, you still see them sometimes. This is a terminal reheat system. Everything looks the same. The only difference is I have a reheat coil at every zone, and now I can have a thermostat at every zone. So I supply, and this time I'm going to supply, it says here I only have a cooling coil. I could have usually I only do have one cooling coil. So I often will supply 55-degree air, and if I need to, I'll reheat it back up. Okay? And that way I can handle, every zone can get whatever temperature they want. It's a super inefficient way of doing doing air conditioning. It's super inefficient because it's cooling things to 55 and you might be reheating it back to 100. It's like, oh man, what a waste. So one of the main ways we try to save energy in HVAC is we try to reduce the simultaneous heating and cooling. That's why terminal reheats, they're not, they're not naturally 90.1, not at all. It's just not acceptable anymore. Let's move on. Then no one installs them. A variable air volume system is just like a terminal reheat, except the difference is in the terminal boxes. So now what they do is they still deliver this 55-degree supply air, but now they have dampers that will close. So let's say you have a room that it doesn't need full cooling, so let's just close the dampers a bit. Oh, but now it's still too cold. Well, we close the dampers to their minimum position, which might be, let's say, 25% or so. It closes the minimum, but it's still too cold. Then it turns on reheat. Okay, so the reheat comes on after the dampers have closed to the minimum position. So this is a much more, let's say, economical way, but there's more to it. I guess I haven't told you everything, but it's more economical because now you're reheating less air. Instead of reheating all the air like a terminal reheat, you're reheating just a portion of the air. So we only heat when we are at a small percentage, like 25%. But the thing that's kind of neat about these systems is as the dampers close, the static pressure in the supply air line builds up. And as it builds up, there's a static pressure sensor in this line, which tells a variable frequency drive to slow the fan down. Okay, so what do I mean? I don't know if I'm going to be clear on this, but I'll try. So often these VAV systems, variable air volume systems, will have a static pressure set point. It might be 1 inch, 2 inches, something like that. And that the fan will vary to maintain that 1 or 2 inch static pressure setting. As the dampers in the rooms close, the static pressure builds up and in the lines will build up and the fan will slow down. As the dampers open, then the static pressure will get lower and the fan will speed up. Okay, so it's a pretty clever system and it's a lot more efficient. And so now you're saving not just on less reheat and less cooling, but you're also saving on the fan because the fans are not running full. Here's a picture of a VAV. I guess it doesn't have the the outside air and return air, but that's okay. The only difference here is we have at the bottom, it says, so in the middle underneath the fan, you see speed, and it's like 78.3%. So the fan's not running at full. And here you also on the right-hand side bottom, you see the static pressure. So they have a set point of 0.8, and it's right now they notice 0.807, which is pretty darn close. So it's varying the fan to meet their 0.8 inch static pressure set point. Okay, so this is what a VAV reheat box looks like. So these are the terminal boxes that are in the ceiling at every zone. On the left is a damper. I mean, you got to look hard to see it, but On the left, you'll see that round tubular-like thing that goes into the box. And on the inside of that, you'll see a damper, which is a circle, which will open and close. Okay? And then you'll see in the middle, that's my heating coil. So I have the hot water that's coming to that. Or it could be steam. And then the air will pass through. This is a dual duct system. So a dual duct system, these also no one installs anymore. I guess, actually, I do see some. I take that back. But so everything on the left is old news. We've talked about that, the economizers and all that. But what's different is we have these two ducts. So on the right-hand side up top, we have a hot deck and a cold deck. Now, I wrote 110 and 55 degrees. Those are typical temperatures that they're going to heat and cool this air to. So now what they do is they'll send two different sets of ducts to every zone, and then they will mix the right amount of hot and cold air to get the correct temperature for each room, and then everybody's happy. Okay. Now, well, we'll talk about ways to be more efficient later. But one thing that can be really inefficient with a dual duct is, why are we, again, well, let me just say it different. Now we're doing all this simultaneous heating and cooling again. That's where you waste energy. Why, if I wanted 60-degree supply air, do I have to heat the air to 110? That's dumb. So that's why this can be very inefficient. So here is a picture of a dual duct on a BAS system. So the stuff on the left is all old news. You see, sometimes I don't have dampers showing, either they don't have dampers or I don't know. I really don't know how this works. But let's ignore the left. What's important is what's on the right bottom, and that is I have a hot deck and a cold deck. So right now they have a set point of 70. So the hot deck, they're not heating to 110 or 100, and I'll explain that later. But the cold deck, they are heating to 60. Okay, let's move on to the next one. So this is what a dual duct mixing box is. So it will take air from the hot deck, so that would be one of these two, air from the cold deck, and then there's dampers which will modulate how much air from each of those two decks goes into this mixing box, and it will deliver air into the zone. All right, so let's talk about being efficient. The best way, I know this sounds silly, but the best way to save energy in HVAC is just don't run it all the time. That's number one. So turn things off. That's number one. Now, there's places where maybe that doesn't make sense, like in the southeast or in really humid climates. If you turn things off, then you might have some humidity issues in the building, and who knows. And the last thing you want is mold. And mold is, if you have an energy efficient building with mold, pretty soon you're not even going to have a building, and that's a bad investment. It's better to have no mold and waste energy. So maybe scheduling turning things off is something you might not be able to do in some areas of the country. You sure can in California. It's not going to be a problem out here. But what you can do instead is something called night setback. Some people call it setback setup, and that is in the off hours. Let's say everybody's in the building till 6 o'clock at night. Then how about from 6 at night till maybe 5 in the morning, we'll change the cooling temperature set point from, we were trying to cool to 70, now we'll cool to 80 or 85. And instead of running the fans 100%, we're going to let them cycle. So typically a night setback will increase the cooling set point, so there's a lot less cooling to do, and it will cycle the fans. It'll let the zone just drift. It was at 70, and over maybe 6 or 8 hours, it might get up to 80 degrees, and then the fan will just cycle on and bring it back to a manageable temperature. So just will cycle to keep this set point. So that's a night setback, and also you can have night setbacks for heating as well. So instead of heating to 70, maybe we will just heat to 55 or 60. So it will allow the building to drift down without having to run the fans. Okay, so night setback will save mostly fan energy, but it does save some cooling and heating energy as well. There's another thing called optimal start-stop. Some people think it's don't like it. They think it's terrible. You hear that from facility people from time to time. Theoretically, it sounds great, and I've also heard people, especially from ESCOs, saying it works really well. So one of the things that's cool is, let's say everybody really does go home at 5 o'clock, then you can turn your fans off, your air handlers off at 4:30, maybe 4:20, and that would be an optimal stop. They're not going to notice as the air in the zone slowly drifts from 70 or 72 up to 75, over that half hour. They're not going to notice, and so you don't need to run the fan. That's easy savings. So, but what an optimal stop does is it will use a computer algorithm, and it will, which learns, and it will, maybe try. It's like, well, let's turn it off 30 minutes early and see what happens. Oh, it's well, that worked. Let's try 40 minutes early. And so it looks at the zone temperatures, it looks at the outside air temperatures, it looks at the and it looks at the past, all its past tries at doing this, and it will learn and come up with the best time to turn off the air handlers. And it does the same for starting. It's like, okay, if everybody shows up at 6 in the morning, when should we start it? Should we start 4, 5, 5:30? And it will look at the outside air temperature, the zone temperatures, and its past experience trying this, and it will decide when to start the air handlers. So that's optimal start stop. It's real common. Hot deck, cold deck reset. So that's in those dual duct systems. Remember I said, why would you heat the hot deck to 110 when you're cooling the, the building, most of the zones want 60-degree air. Well, you don't have to heat it to 110. You can do a reset. And a reset might be something like, look, if the outside air temperature is, let's say, below 70 degrees, let's not heat it to 110 anymore. Let's just heat it to 80, something like that. Now, I really simplified it. Basically, they'll say, if it's below, let's say if it's below 65, we'll set it to, so the outside air temperature is below 65, we'll set the hot deck temperature to maybe 70 degrees, and then have a linear, geez, I don't know how to describe this without a picture, but have it, let's say, modulate up from, oh boy, I'm confusing myself. So if I'm confusing myself, I'm confusing you. So I'm just going to keep it real simple and just say what they're doing is they reset the hot deck temperature based on outside air temperature, or they might do it based on a zone temperature, like the hottest or coldest zone temperature. A cold deck reset does exactly the same thing. Okay, another thing I guess I did talk about, I do have on here, is heating and cooling lockouts. So that's another thing. If you have a dual duct system, you might just say, well, how about this? If it is colder than 70 degrees outside, no, if it's warmer than 70 degrees, just turn off the whole boiler. We don't need any boilers. We don't need any hot water. Forget it. And then the hot deck will just be the return air temperature, whatever is the return from the zone, and then the cold deck will be 55, and then we'll just deal with it that way. So that's what's a heating lockout. And a cooling lockout's the opposite. Let's say it gets below 70 degrees, or no, let's say below 50 degrees, you might decide we don't need any cooling below 50, and so you might lock out the cooling, and then the cold deck temperature would be whatever the return air temperature is, and the hot deck temperature would still be its 100 or 110. Those are on dual duct systems. Now, a lot of people will convert dual ducts now to, or some will, to dual duct VAV. That's kind of complicated. You can do it. It's complicated, and sometimes that leads to controls issues and problems. But I'm sure some folks have done this successfully. Next one down, supply air temperature reset. So that would be for a VAV system where they're providing, let's say, I said they provide 55-degree air. That's a standard set point. But you know what? And then they might have a reheat at the different zones where they're going to heat it up to maybe even to 100 or 110 degrees. Well, why not instead just say, well, how about this? If it is cold outside, let's say below 50 degrees, let's not cool the air down to 55 anymore. Let's cool it to 65. And then we don't have to reheat it as much. So then 65 to 100 degrees is only a 35-degree increase in temperature rather than 55 to 100, which is a 45-degree temperature difference. So we're reducing the amount of simultaneous heating and cooling. And that's what a supply air temperature reset does. It's real common, ECM. A static pressure reset is becoming common too, and what that does, that's for VAV systems, and that's kind of complicated, but I'm going to try to explain it really simply, and that is that, what it does is it will, instead of having a constant, let's say, static pressure set point of 1 inch, where VAV fan, or I'm sorry, the fan is modulating to make that 1-inch static pressure set point. The set point can actually modulate and go down. So if all the dampers are, gosh, I got to make sure I get this right. I think if they're all like closed or mostly closed, then they can like, well, maybe we can, see, I don't know if I got this right, but we'll try it. Then maybe we can modulate the temperature, the static pressure set point down a little bit and lower the fan even more. So it looks at like the low zone, the damper that's the most open, and whatever that position is, and it will modulate based on that. And there is fan savings that can be had there and simultaneous heating and cooling savings. I talked about lockouts and block dampers. You don't see that very often, but occasionally. And it makes sense. So with air handlers, sometimes they serve many, many zones. And some zones are, like one zone might be a 24-hour zone, like it's maybe it's a police station. And most of this air handler serves a bunch of offices, which everybody goes home at 5 o'clock. But it also serves the center that's open 24/7 with all and the jail, so that they have the jail, and then they got all the people who take all the phone calls. So one air handler is serving all of that. But you know what? If we could just have a damper that would close, and then we don't have to send air to the offices because there's no one in there anyway, then we can slow down the fan, and then we could provide less air. We can save fan energy, we can save reheat energy, and we can save cooling energy. That's what a block damper does. So you would schedule it to turn off or close dampers in the ducting so that some zones are cooled or heated only at certain times. So those are some control strategies that people often do. You probably run into these all the time. I'm thinking that my audience here is mostly HVAC folks, and or not HVAC, M&V folks, so they see these terms all the time. And I'm hoping that this actually helped you to understand some of the stuff that you're hearing.